All right, welcome to Carlson Chem Session 2. We're still on acids and bases. Hope you are all well, staying safe, and being smart about your choices. But I do really hope you are all well, that if you're needing any help, you're reaching out. So we are going to keep going with acids and bases. Hope yesterday was helpful. I do want to know how to make this better, how to improve. So I'm not a professional video teacher, so I'm just doing what I think is necessary for you to keep moving forward. I do want to say I know money is tight and all that. I mean, I do recognize that, but I also recognize the situation we're in requires you to even more be a self-learner, self-starter. So if you don't have this book yet, if at all possible, economically, try to get this book, Crash Course, the latest version. I also know that Amazon is like postponing non-essential items, so it might be a little harder to get. And because of that, if you don't have it yet, you would want to order it now, sooner than later. Anyway, try to have a study guide that you are following and getting geared up on, because unless College Board changes things significantly, I mean, even if they extend it a week or something, we still don't have very much time. So try to get that going. I'm going to jump in on page 7 of the notes. These are notes from Adrian Dingle to give credit where credit is due. And I also want to thank again my son Zachary, who made this whole thing possible. So, all right, weak acids and bases, Ka and Kb. We have the weak acid dissociation here. We're just going to jump to the board here, weak acid. So again, we did stuff like this yesterday. We got our weak acid plus water, okay? And we're going to be in equilibrium with the hydronium ion and the anion. So again, just to review, knowing that this is our acid, in terms of conjugate acid-base stuff, knowing that this is our acid, then acids are proton donors, they're H+ donors, so this is going to give the hydrogen, and the water is going to take it. So this is our acid, this is our base. On the other side, once this gives the proton or the hydrogen, then what's left is the anion, and so this is our conjugate base. So acid, conjugate base. In this case, water is acting like a base, and on the other side, the hydronium ion, of course, is the conjugate acid. What we're talking about right now, though, is if it's weak, then we're setting up ice tables. If it's a weak acid, then we're setting up ice table equilibrium equations. And so if we have some initial X amount here, is the way he's got it written out here, and we don't have any here. And then the change, now, of course, for water, we don't care. It doesn't matter what water's doing. It's a liquid. We're not tracking its concentration. So the change here would be minus a small x plus a small x plus a small x. These are both the same because of the stoichiometry, 1 to 1 to 1. And so at equilibrium, this is big X minus little x, and then this is just x and x. So my Ka value would be x squared over x minus x. Nothing for water, because water is a pure liquid. Now, one of the things that we're going to be doing a lot of is saying that the amount that gets dissociated is negligible compared to the initial amount we started with. And we'll see that with our Ka values. If our Ka values are very small, 10 to the -3, -4, -5, up to -10, if these values are very small, then that means hardly any got dissociated. If hardly any got dissociated, X is tiny, especially compared to our initial amount. So when we say x is negligible, we can't eliminate this x and say the numerator is 0, but we can eliminate this one and say this one just goes away. We don't care about that one. So Ka and Kb essentially normally become x squared over whatever our original amount was for the stoichiometry. So you have the equations written there, Zach. You can scroll down to those 3 boxes. You got our equations there. The reason Ka, let me write that out here. The reason you see on there Ka is equal to H3O squared. Ka, your middle box there looks like this. And HA. What this is saying is that in terms of amounts, whatever the amount of hydronium that comes across, that's the same amount of anion that comes across. So it's as if we can just square the hydronium ion, which is what's happening here. And then of course pKa equals the negative, just like pH equals the negative log of H plus, just like this, then that means pKa equals the negative log of Ka. And that's the second or the third equation you see on page 7. All right, so let's do some of these tasks here. Let's step through these tasks. This is task 8.3, number 1 on page 7. And it says, if ethanoic acid has a pKa of 4.74, so before I erase this, I might want to use some of this. So actually we'll go over here and I'll do it over here. Before I erase this, remember you and your peers are your greatest resources. I'm the second, whatever I'm doing here with the online work, and then use College Board. I would add to that I'm going to say crash course. The crash course book. Hopefully you've been keeping up with the assignments so far. Okay, but let's work, before I erase that equation there, let's work some of the equations over here. So number 1, if ethanoic acid has a pKa of 4.74, what is the Ka? All right, again, pKa is the negative log of the Ka. So I have 4.74 equals the negative log of Ka. So in my calculator, to do this, I'm going to do the inverse log. So I'm going to say inverse log, and my calculator inverse log, and then negative 4.74. What that looks like on your screen is going to be 10, and then where the x is, you're going to put in, you're going to type in, once you see that 10 and the flashing x, you're going to put in negative 4.74. Okay, Zach, can they see this okay? Is this on the screen? Yeah. So when you do that in your calculator, your answer is the Ka is 1.82 times 10 to the minus 5. 1.82 times 10 to the minus 5. So in the calculator, again, if you're given pKa, just type in inverse log and then the negative of the value, and you're going to get Ka. So number 2 is if propanoic acid has a Ka, what's the pKa? You're just doing the negative log. So the inverse of that, or I should say the reverse of that, number 2 in the task, is if the Ka equals 1.38 times 10 to the minus 5, then again, pKa is negative log Ka. So just plug it into your calculator. Negative log of 1.38 times 10 to the minus 5. Just plug that in and you're going to get the pKa equal to 4.86. All right. So if you have any questions about these, you can be asking them through the chat or when the YouTube channel is watched later. And aside about that, to make sure we understand what's going on, for if you tell others who aren't online yet that these are being recorded and live on Twitch. And I sent out that link yesterday, and then my son is loading them up to YouTube after the fact. All right, but there's places on both of those that you can ask questions. So number 3, which is stronger, propanoic or ethanoic? Well, the Ka of ethanoic is 1.82. 1.82 times 10 to the minus 5. The Ka of propanoic is 1.38 times 10 to the minus 5. So which one is stronger? Whichever Ka is greater. So 10 to the negative 5 are the same, but 1.82 is greater than 1.38. So ethanoic is stronger than propanoic, simply because the Ka value is greater. Because if the Ka value is greater, what that means is, if the Ka value is greater, that means more of it came across. And the measure of an acid is how much hydronium do we have? How much hydronium do we have? If the again, understanding what Ka is, what K is, it's the products over the reactants. So if there's more product, K gets bigger. If K is bigger, more of the hydronium got dissociated. It makes it stronger. All right, so that's number 3. Number 4, what's the pH of a 1 molar solution of ethanoic acid? Okay, so here we can use our ice table over here just as a generic example. So let's just say this is ethanoic acid. Let's just call this ethanoic acid. When ethanoic acid, a weak acid, is in equilibrium, you're going to get the hydronium ion and your anion. And so if this is 1 molar, then we're changing X to be 1. So if X is 1, these are still zeros. We're still getting off minus X, and we're having X is over here. So the what is the pH of a 1 molar? So we know that the Ka of ethanoic acid from above is 1.82 times 10 to the minus 5. And that's going to equal X squared, X times X, X times X. That's going to equal X squared over, instead of this being just X now, we know this is 1. So this is a 1. Okay? And so this is 1 minus X. Now this is where we're saying, with most of these weak acids, we can say that X is negligible, and it follows the 5% rule. If 5% or less came over, then we can disregard X down here, or we can say it's negligible. All right. So what we're going to do is say let's assume that that's true. Let's assume that 5% or less came over. So we're going to say it's negligible. So we're not going to worry about that. So 1.82 times 10 to the minus 5 equals X squared over 1. Of course, that means it just equals X squared. So just take the square root of this. Right? So take the square root of both sides. And if you take the square root of both sides, X is, which, by the way, don't forget, X is your hydronium. X is the hydronium concentration. So just solve this for X by taking the square root of both sides. When you do that, you get 4.27 times 10 to the minus 3. 4.27 times 10 to the minus 3 is your hydrogen ion concentration. Now what it's asking is what's the pH, okay? So don't forget the pH is the negative log of what you just did. Negative log of 4.27 times 10 to the minus 3. So that's just calculator work. Plug it in and you should get 2.37. pH equals 2.37. That's your answer for task 8.3, number 4. All right, any significant questions so far? No? Okay. If you have any questions you can be asking along the way, I can answer them on the spot. But this is task 8.3, number 4. Okay, so now number 5. I just going to erase some of this. So for number 5, calculate the Ka of a 0.1 molar of a weak acid, just any generic weak acid. So now it's 0.1. Instead of 1, it's 0.1. Well, 0.1 is still much greater than what comes across generally. 1/10 is still going to be generally much greater than what comes across as X. It tells us that the H plus is 1.75. So this is H plus, so it tells us that this is 1.75 times 10 to the minus 3. 1.75 times 10 to the minus 3. And so that's what this is as well. Tells us what that is. 1.75 times 10 to the minus 3. Okay? So again, those of you who are already, light years ahead mathematically than I am, you already know that you don't have to do all of this to necessarily understand that you can that you know that Ka is going to be this number squared, this X, it's going to be this number squared, 1.75, because that's how much came across, over, okay, 0.1 minus this number. Now, because we have the number, we can go ahead and use it. Now, I didn't do this when I was preparing for this, so let me punch that in the calculator as I move across the screen here. Let me kind of verify this for you, and then you can see 1.75 negative 3. So this number becomes, so this is going to become, again, 1.75 times 10 to the minus 3 squared over, this becomes 0.09825, okay? Which is less, so let's do this. Let's do 1.75, second function, negative, wait, 1.75, second function over the negative 3 divided by 0.1 times 100. So again, those of you who are more numerically minded than the rest of us already knew, probably in your head, that this number right here is 1.75% of this number. So how much hydronium came across? 1.75% of this. If it's less, if it's 5% or less that came across, we can count this as negligible. So if you're given the number, all of the numbers, then you can plug all the numbers in. But if you're solving it without X, then you can just take X out of there. All right, all all of that this is all in explanation of understanding the 5% rule. So what this comes down to is just solve this in the calculator. Just solve that in the calculator. And so when you do that, you're going to get 1.75, second function e, -3 squared. And you're going to divide that by 0.09825. You're going to get your Ka to be 3.12 times 10 to the -5. That's your Ka. All right, that's number 5 on task 8.3. Any questions? What timer is it? How much time have we used?
It's 11:20.
Okay. All right. So now let's talk about number 6. Calculate the Ka of a solution of 0.25 with a pH of 5.11. Okay. So for this one, well, let me erase this stuff here. So for number 6, we know that it's 0.25 molar. We know this is 0.25. Now you don't necessarily need to write all this out to solve these once you have more experience doing this. But number 6 looks like this. So we have the pH is 5.11. If the pH is 5.11, I can figure out the H plus by taking the inverse log of -5.11. So H plus would be 10 to the -5.11, and that is 7.76. So H plus is 7.76 times 10 to the -6. That's our H plus. So that means my Ka, because it's asking for Ka, is going to be this number. This is my X. That's how much came across. So that's going to be 7.76 times 10 to the -6 squared, all over 0.25 minus X. Well, X is tiny. It's so small, I'm just going to forget about it. Let's say it's just over 0.25. So that's just calculator work, and you're going to get 2.41 times 10 to the -10. That is number 6. Okay? All right. So on the next page, page 8, this is Kb. We were looking at Ka, now we're looking at Kb. It's the same idea, but now we're tracking OH instead of H plus. Or we're really able to track both. We're always able to track both. So this is ammonia, NH3 in the water, and it's going to go again in this time though. If we know we're dealing with, like, if you memorize that ammonia is a base, NH3 is a base, it's a weak base. We'll talk again about what's weak and what's strong tomorrow. But if you know this is a weak base, then water is going to act like an acid. And if this is a base, then bases accept a proton, or they accept a hydrogen ion. So if this accepts one, it's going to take it from the water, and this becomes NH4. So if this is a base, this is its conjugate acid. And if this is a base, water's acting like an acid. And it gave up a hydrogen, so what's left? OH. And again, these are aqueous. The weak base is aqueous. the conjugate acid is aqueous, conjugate base is aqueous, and the water is liquid, so we don't consider that. Okay, so we can erase all of this and look at some new problems here. So everything I've said about Ka, everything that was on page 8 is the same as page 9, so I'm just going to jump to the tasks. Okay, if ammonia has a pKb of 4.75, so this is task 8.4. Task 8.4 and number 1. If ammonia has a pKb of 4.75, what is its Kb? Again, I'm going to take the inverse log. So 10 to the negative 4.75, plug that in, you get 1.78 times 10 to the minus 5 with the same exact thing as Ka. So let me pause here and say Ka, the A means acid, so it's the equilibrium constant for an acid. Kb, the B means base, so it's the equilibrium constant for the base. So if you are given a Kb, it's tracking the dissociation of a base. If you're given a Ka, it's tracking the dissociation of an acid. So this is the strength of the base, okay? You can figure out what K, like as soon as you have one, you have the other. Because don't forget that Kw is equal to Ka times Kb. Kw is equal to Ka times Kb. So whenever you have one, you have the other. Because Kw and of course this is temperature driven. This is temperature driven, that Kw at room temperature is 10 to the negative 14. So as soon as you have one, you have the other because Kw is 10 to the negative 14. It's a constant. All right. If you have a question on that, I can clarify. But you should always keep in mind that Kw equals Ka times Kb. The equilibrium constant of water is equal to the dissociation of the acid times the dissociation of the base. All right. So number 2 is the same as the number 2 on the previous page. Kb is 4.38 times 10 to the negative 4. What's pKb? Again, pKb is equal to the negative log of Kb. So just plug it in. Negative log of 4.38 times 10 to the minus 4. Just plug it into the calculator, do the magic there, and you get 3.36. That's the pKb, 3.36. So which is stronger? Again, if the Kb, so this is number 3 now, if the Kb of which one is this? 4.38. If the Kb of, this is methylamine, okay, is this, and the Kb of ammonia is 1.78 times 10 to the minus 5, okay. Kb of methylamine is 4.38 times 10 to the minus 4. Kb of ammonia is 1.78 times 10 to the minus 5. You're just asking yourself which, and if it wants to know which is stronger, you're just asking yourself which one is bigger, which number is bigger. Of course, it's this one, 4.38 times 10 to the minus 5, because we're looking at the exponents here. This is a larger number, so methylamine is the stronger base. This is the stronger base. That's for number 3. Okay, what's the pH of a 0.44 molar? This is number 4. 0.44 molar. So we can come over here and say the ammonia is 0.44. Okay? And so this is 0.44 minus X. Okay? All right, that's how that, if you needed to set up the ICE table to prove your work, this is what it would look like. However, if you already understand how this is going mathematically, okay, it wants to know the pH. So it wants to know, the only way I can get to the pH is to get the negative log of the H plus. So what I really need to know is X. This is what it's really asking me, is what's X? Because X is H plus. So really what I'm going to find here with this X, I'm going to find the POH. POH is negative log of the OH. Don't forget that. pH is the negative log of H plus. POH is negative log of OH. And pH plus POH equal 14. So you have to keep track of are you looking at an acid or are you looking at a base? So for number 4, what's the pH of 0.44 molar solution of ammonia? You absolutely need to memorize that ammonia is a weak base, and we'll talk about how to figure out what's weak and what's strong tomorrow. But if you know that this is a weak base, then you know when you solve for X, you're solving for hydroxide. You're absolutely solving for hydroxide. So let's just do it. So we already know what the KB of ammonia was given to us above, and it is 1.78 times 10 to the minus 5. Now, I can look at this number and say this is 0.0000178. This is a tiny KB compared to 0.44. So I know already in my head that when I compare negative 5, the exponent of negative 5 to 0.44, X is going to be less than 5%. So if X is less than 5%, I don't have to deal with it. So that means my equation becomes X squared over 0.44. And what I keep trying to say is that you can set up this whole thing, or mathematically you may already just be able to jump right to this. And so solve this for X. Okay, you have 1.78 times 10 to the minus 5 equals X squared over 0.44. Just do the algebra, solve that for X, but remember that X is OH. X in this case is the OH. When you solve for that, you get hold on a second here. Oh, this is number 4. Okay. This OH is 0.00280. Okay, molar. So then that means the POH is the negative log of that. Negative log of 0.0028. And that is, well, I already did the math. So let's go ahead and figure it out here. That's going to be negative log of 0.0028. So this POH is 2.55. I don't want the POH. I want the pH. Well, this here. So take this, take 14, subtract 2.55, and you're going to get the pH is 11.44. That's 4 or 5. I guess it should be 11.45. 11.45. So the answer to number 4 is 11.45. All right. So before I do any more, well, I'm not going to do any more. So instead of doing 5 and 6, I'm going to leave 5 and 6 for you to do, and we can talk about them tomorrow. So try to do task 8.4, number 5 and 6. I've done everything else up until that point. And what I want you to do is in the notes, Zach, if you could scroll down, read page, so for tomorrow, answer those 2 tasks, and then on page 9, so read all of 9, scroll down, read 9, 10, 11, and 12. So read pages 9 through 12 and do those 2 tasks. And also, we don't have it up on the screen down there, but you had picked up this as part of the notes packet that I'm showing you in the camera here. Also read up on this, okay, this small packet here. So Zach is scrolling the main packet through page 12, and also read about titrations, topic 4F, before we get to the next one and that one. So you got a lot of reading to do and these 2 tasks, plus hopefully you're caught up on the other worksheets. I've sent through Remind all of the keys to those. But if you have questions, please ask them through, if you watch this on YouTube or other people do, because you could be asking questions as I'm talking live or later on YouTube. I think those might be easier platforms than Remind. I think that's what I wanted to say. We got homework for tomorrow. We're going to stay caught up. Right now, I'm going to say we'll do it again tomorrow at this time, 11 a.m. Hope this is helpful. Do you have any questions scrolling there for me? Okay. So I think that's a wrap for Wednesday. Have a great day. Thanks.